Okay, hey, we're back. Welcome to the last video of this first lesson here on thermal energy from chapter 21. Today, in this last little video, we're going to talk about specific heat capacity, right? A shortened symbol for it is CSP. There's actually a formula for calculating the specific heat capacity. Every material has a specific heat capacity. So what we're going to do is we're going to learn about this concept and try to apply it to actual important uses, purposes for knowing this concept, and even learn the basics of how to calculate it. Now, before we go too far, I realized that I could have thrown a couple of other terms into that last video where we were dealing with thermal equilibrium and thermal energy and those basic terms like heating. I should have thrown in there the concept of the calorie and the concept of the joule. A calorie and a joule are thermal energy units for measuring the amount of thermal energy that is in some type of substance or in some type of system. The calorie is defined, and I'll write this down for you, as the amount of thermal energy needed to raise 1 gram of water 1 degree Celsius. Right, hopefully you get that. It's a little bit of a shortened version. The amount of thermal energy needed to raise 1 gram of water up 1 degree Celsius. Or technically you could reverse that. The amount of thermal energy that's needed to be lost to decrease the temperature of 1 gram of water by 1 degree Celsius. So if you put water on the stove and you're heating it up to make mac and cheese, that would be adding calories of thermal energy to it. Right? Find out how many grams of water you have and how many degrees Celsius it changes, and that's how many calories you used. Or if you're making ice cubes, put the water in the freezer and find out how many grams of it you have and find out how many degrees it goes downward, and that's how many calories you lost. Now the joule is just another thermal energy unit for measuring with. The thing is, I don't use it very often, although your book will use it. Other scientists will use it. I think I have a video for you to watch in this lesson, and it'll actually be using joules. It's really not a big deal. It's like measuring in feet or yards, or measuring in yards and meters. They all measure the same exact thing. It's just a different unit. So 1 yard is 3 feet. Well, 1 calorie is 4.184 joules. You can do a pretty basic conversion on that, and I think you'll be able to get that. So let's get into specific heat capacity now that we've got some of these terms that are going to relate to it. So let's break the word down. Let's start with the concept of heat capacity. Right? Every piece of material has the capacity to hold thermal energy or even transfer thermal energy. Right? Everything has a specific capacity. This is a simple illustration, but here is what is about a 150 milliliter beaker. It has the capacity to hold about 150 milliliters of liquid. Here is a 1 liter beaker. It has the ability to hold 1 liter, 1,000 milliliters. It's, I don't know, 5, 6 times bigger than this little beaker. Each of these beakers has a capacity. Every piece of material has a capacity to handle thermal energy. Some substances get hot very, very quickly, and some get hot very, very slowly. Some materials can absorb lots and lots and lots of thermal energy, and they can hold on to it really well. They're good at insulating. Some materials, they don't absorb a lot of thermal energy. They get hot fast, but then they can dump it out. Right? Every material is different, and that's where this becomes very applicable. Since every material has a different capacity, you can use every material for a different purpose, and we do use every material for a different purpose. So one of the best examples that I like to use is spacecraft. spacecraft have to leave the Earth's atmosphere and re-enter the Earth's atmosphere, and there's a ton of friction, which means there's a lot of thermal energy involved in that situation. There's more upon re-entry because upon re-entry they're going faster, right? So they have to build the spaceship, the rocket, whatever you want to call it. They have to build it out of material that is thermal energy resistant. They can't just build it out of regular old aircraft aluminum. It would be way too hot and it would melt down, right? It would burn up, and then everything that's inside and every human life that's inside would die. So they've had to figure out, what can we build the space shuttles out of? They build it out of a material that is very resistive to thermal energy absorption, and it doesn't melt down very easy. So every material has a different specific heat capacity. The reason specific comes in is because every material is going to have its own specific ability, right? A piece of plastic, here's a piece of PVC, is going to have a different capacity for thermal energy than this piece of metal. And this is a piece of tape on the end. Don't worry about that. Every material has a different capacity, and that's how you choose what they're used for. So, something that has a very high specific heat capacity will typically heat up very slowly, but it will typically be able to hold a lot of thermal energy, and it will typically hold it for a pretty long period of time. A good example of that is water. Water has a specific heat capacity of 1. That's not the highest specific heat capacity that's out there, but it's pretty high. And it takes water a decent amount of time to warm up. You don't just put water in a pot to make mac and cheese and 30 seconds later have a boiling pot of water. It takes time to heat it up. But then that water actually stays pretty hot for a period of time. You don't just turn the burner off and 30 seconds later have a pot of water that's safe enough to put your hand in. Right? It absorbs a lot of thermal energy, and right, as it absorbs that thermal energy, it holds onto it. But something different is a piece of metal. Here's one of these metal poles from back here in the lab. Right? This piece of metal will absorb thermal energy very, very quickly. Right? But it doesn't have the capacity to hold as much as some other substances, right? Right? It warms up very, very quickly, gets very, very hot, but then you can let a piece of metal go and just sit, and it will actually cool down pretty quick. Oops, sorry about that. So think about a piece of aluminum foil. If you've ever used a piece of aluminum foil around the outside of a baked potato, right, and you've baked it in the oven, the potato gets to 350 degrees. The aluminum foil on the outside gets to 350 degrees. You take the aluminum foil off and let it sit for 10 seconds. You can crumple it up in your hand and it won't burn you because it's got a low specific heat capacity. It absorbs the thermal energy in the oven, but then you open it up and it's very, very small, very, very light. And what it does is dissipates that thermal energy very, very quickly because of that low CSP. And boom, you can crumple it up, use it, throw it away. It doesn't burn you, doesn't burn the garbage, and it's perfectly safe. Right? Different materials do that differently. So just a couple basic things to remember. Metals have a low CSP, heat up very, very quickly. Water has a higher CSP, heats up very slowly, but holds that thermal energy for a fairly long period of time. Something that has an even higher specific heat capacity than water is oil. Oil has a huge specific heat capacity. It's much higher. That's why oil boils at a much higher temperature than water. That's why we use oils as a heat sink, right? They use oils in big electrical devices to absorb thermal energy to help keep them cool, right? Because it can absorb a lot of thermal energy and it doesn't boil very easily. So every material has its own specific heat capacity. And if we want to calculate the specific heat capacity, I think this is going to be the last thing that I mentioned. We want to calculate the specific heat capacity. What we need is this basic formula. The specific heat capacity is equal to Q over M times delta T. All right, so first off, what is Q? Q is the calories, or technically joules. I prefer calories. Calories of thermal energy that are absorbed. So if we want to calculate the specific heat capacity of this piece of metal, we would need to know how many calories of thermal energy it absorbed. Did it absorb 10 calories, 100 calories, 500 calories? If we get that number or calculate that number, we can put it at the top of the fraction. Then we need to know the m, that's the mass. Right? You would take the object that you're trying to measure the mass, measure the CSP of, and put it on a scale, get its mass. And then delta T, that's the change in temperature. If we know, right, the number of calories that the object absorbs, the mass of the object, and the temperature change of the object, we can figure out its specific heat capacity. And once you know its specific heat capacity, you know whether it's low or high or medium, you can then choose how to use that material. Do we use that material for an insulative purpose, a conductive purpose? Is it safe to put on the outside of the space shuttle? Does it need to be kept away from heat sources? Can it be a good heat sink? A heat sink is something that absorbs thermal energy and then dumps it away to somewhere to get rid of it. Can it be used as a radiator fluid in a car? There's lots of reasons why we would want to know the specific heat capacity. All right, so there are a few exercises that I hope are very explanatory for you on the LMS, and another video that kind of gives a lab application to this concept of measuring the specific heat capacity. It's a little bit more complicated, and if we need to, we'll go back over it, or we will do it when we finally get back to class. All right, have a good one. I'm going to step aside and let the screen roll for a minute so we don't have to see ads. You can pause it and stop at any time.